Swayam Prabha. Digital India. Educated India.
Hello everyone. Today it is my third lecture of the module 10. So far I was discussing about the application of membrane theory in pressure vessels and tank in this module. Today I will give a further application of membrane theory in the surface of revolution in the form of hyperboloid of revolution. So, that type of shell is very common in cooling tower in thermal power station, and we will see how this type of shell can be analyzed with the help of membrane theory. Okay. So, topic of discussion is hyperboloid of revolution and its application to cooling tower. Okay. So, cooling tower that are actually a very essential part of the thermal power station, and it is having a hyperbolic paraboloid type of shell. So, that is constructed in concrete made of reinforced concrete and steel, and has to resist the self weight and other imposed load. So, therefore, the design of this type of cooling tower is very important and significant for the safety of the industrial operation, and the design is generally done using the membrane theory of shell. So, we have discussed the membrane theory of shell, and we have seen that in case of membrane theory, the membrane forces, that is in plane forces n phi n theta and membrane shearing forces n theta phi are of significant. But in case of shell with axisymmetrical loading, we do not have to consider this n theta phi or n phi theta. Therefore, it becomes a problem of finding only two unknown variable n theta and n phi, which are the circumferential stress and meridional stress respectively. Once you find this n theta and n phi though it is a membrane force and expressed as force per unit length, but when we convert it into stress unit, that means the n theta and n phi is divided by the thickness of the shell, we get this the stress, corresponding stress. So, n theta divided by thickness of the shell, say h, will give you the circumferential stress, which is also commonly known as hoop stress, and when n phi divided by h will give this meridional stress, or it is commonly known as longitudinal stress. Okay. So, hyperboloid of revolution of one sheet is formed when a hyperbola is revolved around a vertical axis of rotation. So, this is the vertical axis of rotation and this is the hyperbola. So, when it is rotated around this vertical axis of rotation, the shells of surface of revolution is formed, and it is nothing but hyperboloid of revolution. Okay. Now, we have to know the properties of the hyperbola, that is actually the meridional curve in this case, and it is rotated around the vertical axis of rotation. So, let us see what are the properties of the parabola that will be essential for the analysis of the stresses in the hyperboloid of revolution. So, every hyperbola has two axes of symmetry that you are seeing. The axis of symmetry is your this x axis and this y axis. So, this hyperbola that it is a axisymmetrical shell of revolution. So, whatever load that is applied here is symmetrical about the axis of rotation. The transverse axis, that axis is a line segment that passes through the center of the hyperbola. So, center of the hyperbola is this, and it passes through the center of the hyperbola and has vertex for each hyperbola, that is for meridian. Meridian is rotated about the vertical axis of rotation. So, vertex of the parabola is located at the transverse axis. So, this is one vertex point and another vertex point is there. Okay. So, the distance of the vertex of hyperbola from the axis of rotation is a factor known as a. Now, let us see the hyperbola has a focus. So, one focus is here for this hyperbola, and when it is rotated and it is on the other side, there will be another focus. So, the focus that is lying on a axis, it is lying on a transverse axis, and conjugate axis is the another axis which is perpendicular to the transverse axis. So, y axis is here is a conjugate axis. Okay. Conjugate axis also has co-vertex. So, co-vertex is located by knowing the side of the rectangle. Okay. The center of the hyperbola is the midpoint of both the transverse and conjugate axis. Okay. Now, every hyperbola has two asymptotes. So, two asymptotes you are seeing here, that is hyperbola recedes from the center gradually and its branches become asymptotic, that is you approach this asymptote. So, you can see here in the upper portion as well as lower portion, it is the hyperbolic curve is asymptotic to the straight line. So, asymptotes are straight line passing through the center of the hyperbola. The central rectangle that is formed here is centered at the origin with sides that passes through each vertex. So, one side is this distance between the two vertex, that is if a is the distance of one vertex from the axis of rotation, then the side of this rectangle is twice a. The co-vertex are at a distance from B from the transverse axis. So, if it is a distance of B from the transverse axis, the length of this central rectangle is twice B. So, twice B is the length and twice A is the width. So, we get the size of the rectangle, that is the central rectangle, and the asymptote is diagonal to this central rectangle, that it has to pass through the center of the rectangle as well as through the corner of the rectangle. So, two asymptotes are there and the branch of the hyperbola become asymptotic as it goes away and away from the center of the hyperbola. To draw the asymptotes of the hyperbola, simply draw and extend the diagonals of the central rectangle. So, if I draw the diagonals of the central rectangle and extend it, we will get the asymptotes. So, asymptotes slope is important and it can be easily found by knowing the length and breadth of the central rectangle. Okay. The standard form of the equation of the hyperbola with center as 0 0, center is the origin which is taken as whose coordinate is 0 0, and transverse axis lying on the x axis. So, this is the x axis, conjugate axis is your y axis. Okay. So, then equation of the parabola hyperbola can be written as x square by a square minus y square by b square equal to 1. So, that is the equation of the hyperbola. The length of the transverse axis is 2a and coordinate of the vertices are plus minus a 0, that is on the right hand side towards the positive axis. The focus is located at a distance of c from the center of the parabola, and on the left hand side towards the negative side of the x axis, the focus is located at a distance of c from the conjugate axis. So, the vertex are located at a distance a from this conjugate axis, whereas the focus foci, two foci are there. So, two foci are located at a distance of c from the conjugate axis. Okay. But this distance between two foci and this length of the transverse axis and length of the conjugate axis are related by this relation. So, c square equal to a square plus b square. So, this relation is valid for this hyperbola. Now, you can see here that in the equation of the parabola, a is simply known as this distance, that is the distance of the vertex of the parabola from the vertical axis of rotation, that is the conjugate axis, whereas the b has to be found if we know the distance between two foci. So, if a is known, then b can be found if c is obtained from the distance between two foci. Okay. The coordinate of each foci is plus minus c. On towards the positive axis it will be c 0 and towards the negative axis it will be minus c 0. Okay. The equation of the asymptotes you are seeing that it is passing through the center of the parabola. So, it is a straight line. So, its slope will be b by a, because this side is b and this is a. So, slope is simply b by a, and equation of the straight line is in the form standard form y is equal to m x, where m is the slope of the straight line. So, slope of the straight line is b by a. In the positive direction you will get plus b by a, in the negative direction you will get minus b by a. Okay. So, these properties are essential to solve the equation for membrane stresses. Okay. Now, let us consider the hyperboloid of revolution of one sheet, and meridian is a hyperbola. So, this is the meridian which is a hyperbola, and equation of the meridian can be written as x square by a square minus y square by b square equal to 1, where the a square a is the distance between the vertex of the parabola from the axis of rotation, whereas the b has to be found from the distance of the foci that is also lying on the transverse axis, as the distance between two foci are related by the equation c square is equal to b square plus a square. So, a square is known as the length of the transverse axis, whereas b square has to be known from the length of the conjugate axis. That means, a central rectangle will be there, and in central rectangle the width is 2a and the length is 2b. So, this the co-vertex is located at a distance b from the transverse axis in the upwards direction, and another co-vertex is in the downward direction. It is located at a coordinate 0 minus b. Okay. So, we know all the geometrical parameter of the hyperbola. Now, we can write the equation, where x has to be greater than or equal to a. So, radius of the parallel circle r is equal to x coordinate. So, at any level, suppose we want to find this parallel circle, that is the parallel of latitude you can call it. So, here this x coordinate will give the radius of the parallel circle. Okay. Now, this number 1 equation can be written because we want y to find out the slope and curvature. So, y can be written from the equation 1 as plus minus b by a root over x square minus x square. To calculate principal radii of curvature, we require first and second derivative of y. Now, you can see this type of shell, that is hyperboloid of revolution, is essentially a doubly curved shell, but it is anticlastic. So, due to anticlastic nature, you can see that one radius of curvature, that is center of one radius of curvature is in the opposite direction as compared to other radius of curvature. So, two radii of curvature R 1 and R 2 are shown here, where R 1, the radius of curvature for R 1 will meet the center in the opposite direction, whereas R 2 will meet the vertical axis of rotation at this point. So, they are on the opposite side of the middle surface of the shell. Okay. So, differentiating this equation number 2 with respect to x, we can find the slope. So, dy by dx can be obtained as b by a half x square minus s square raised to the power minus half into 2x. So, ultimately cancelling 2 from both numerator and denominator, we obtain that dy dx equal to plus minus b by a x divided by root over x square minus s square, and dy dx is given as tan phi. Okay. So, tan square phi can be obtained from this equation. Tan square phi is b square by s square into x square by x square minus s square. So, this type of shell is an example of anticlastic shell, which we have not earlier analyzed. We are earlier analyzed a shell which are doubly curved of course, but they were synclastic nature, and in one case we have found that the Gaussian curvature is 0. So, such type of shell is formed by rotating a straight line. Say example is cylindrical shell or conical shell that we have found earlier. Now, here the Gaussian curvature, if you want to calculate, Gaussian curvature is nothing but product of two principal curvature. So, if the radius of curvature is R 1 and R 2, so naturally the Gaussian curvature will be 1 by R 1 into 1 by R 2, and out of that 1 by R 1 will be negative. So, therefore, you will get Gaussian curvature is always negative for that type of shell, and it indicates that it is a anticlastic shell. Okay. Now, from equation 4, we can obtain the x. Okay. So, just by simple algebraic manipulation, we obtain x as s square into tan phi divided by root over s square tan square phi minus b square. Now, this equation can be examined very carefully to see the validity of or the range of x in which x is valid. So, you can note here that if s square tan square phi minus b square is negative quantity, then x is imaginary, which is not possible. So, therefore, from this equation 5 we can impose a condition for this hyperbola that a square tan square phi should be greater than b square. So, which means tan square phi should be greater than b square by a squares. So, this is the characteristic of hyperbolic meridian. Okay. Now, from equation 5 is this. So, here tan phi is again substituted as sin phi cos phi, sin phi by cos phi. So, substituting tan phi as sin phi by cos phi, the equation 5 can now be written as x equal to s square sin phi divided by s square sin square phi minus b square cos square phi raised to the power half. So, that means this term is under the square root. Okay. The second principal radius of curvature R 2 can be easily expressed as R 2 equal to if this coordinate is x or r. So, this x divided by sine of this angle, and sine of this angle is pi minus phi. So, x by sine phi, and sine phi can be obtained because tan phi is known. Once the tan phi is known, then you can obtain the sine phi also. So, substituting the value of sine phi, then we get this r 2 as s square divided by s square sin square phi minus b square cos square phi, or directly you put x is here, x as this quantity from equation number 6. If you put x from equation 6, you will also arrive at this quantity. So, the second principal curvature is known, s square divided by bracket s square sin square phi minus b square cos square phi raised to the power half, and first principal radius of curvature we now have to obtain. Okay. From the equation of this calculus that we know, to determine the curvature we need first derivative and second derivative that we have already calculated. Okay. So, r 1, the other principal curvature, that is the curvature of the meridional curve, which is a hyperbola, and for that meridional curve at this point we have obtained dy dx as well as d square y by dx square. So, with this quantity dy by dx and d square y by dx square, that means first derivative and second derivative of the meridional curve, the function which defines the meridional curve, we can obtain now r 1. So, r 1 equal to 1 plus dy by dx whole square raised to the power 3 by 2 divided by d square y by dx square. So, this is the r 1, and substitute now the value of dy dx and d square y by dx square that we obtained earlier for the hyperbolic meridian. So, substituting these two quantities dy by dx and d square y dx square, that is equation number 9 and 10, equation number 9 and 10 that we substitute here, we will get the r 1 in terms of x and other parameters of the hyperbola. So, r 1 equal to s square into x square minus s square plus b square x square raised to the power 3 by 2 divided by a to the power 4 b. Okay. So, we have obtained r 1 the first principal curvature and r 2 as the second principal curvature. So, product of this 1 by r 1 and 1 by r 2 will give you the Gaussian curvature. Okay. Since r 1 is to be given a negative side, because r 1 lies on the side of the shell's middle surface opposite to that on which the axis of revolution lies. So, axis of revolution lies on that side, center of curvature of the hyperbolic curve at this point will lie on the opposite side. So, therefore, r 1 is negative quantity, and when actual calculation will put r 1 as negative, but this absolute value of r 1 is given as s square b square divided by s square sin square phi minus b square cos square phi raised to the power 3 by 2. So, these two quantities are very important, two principal radii of curvature that is obtained from the first principle of calculus. Okay. So, next we go for membrane analysis of the shell. Okay. The shell here is under the axisymmetrical loading, although it is a anticlastic shell, but it is of doubly curved nature and it is non-developable surface. Okay. So, in this type of shell, under the self weight acting along the surface of the shell, the loading condition is symmetrical with respect to the axis of revolution. So, therefore, the membrane shearing force n phi theta and n theta phi is taken are to be taken to 0, and deformation that is displacement, stresses or loading of the shell is independent of the angle theta. So, thus only two equations of equilibrium are essential to find the unknown quantities, that is n phi and n theta. So, first equation is d by d phi into r n phi minus r 1 n theta cos phi plus r 1 w phi. R 1 is the first principal radius of curvature. Here in this example we have taken the symbol R 1. So, capital R 1 has to be replaced by symbol R 1. This is the general equation we have derived earlier and we are referring this to obtain the membrane stresses n phi and n theta. Okay. So, R is the radius of the parallel circle at certain level defined by the angle phi, and you can see here this n theta and n phi both are appearing in the first equation, but second equation of equilibrium is an algebraic equation and it is given by n phi by r 1 plus n theta by r 2 equal to W r. W r is the component of the load in the radial direction. So, from this equation B, there is the second equilibrium equation in that case. Equilibrium equation here pertains to the balance of forces along the radial direction. So, from this equation n theta is obtained as W r r 2 minus r 2 by r 1 into n phi. So, substitute this n theta here and we will get as now this equation, substituting this n theta value here, we now get this differential equation in this form, and after rearranging. So, this form is d by d phi r n phi sin phi minus r 1 and this is actually it was n theta. So, this value is substituted here. Okay. Then other quantities are there already, and then rearranging some terms of the equation 7 and using r is equal to r 2 sin phi, we now obtain the differential equation in this form d by d phi r n phi sin phi plus n phi r cos phi equal to r 1 r 2 into w r cos phi minus w phi sin phi into sin phi. This equation now has to be integrated. So, again these two terms can be written in this form. So, d d phi r into n phi sin phi equal to r 1 r 2 into w r cos phi minus w phi sin phi into sin phi. So, we have grouped these two terms together, and you can see here the r is nothing but your r 2 sin phi. So, in some of the equation we have substituted r 2 as r as r 2 sin phi. So, therefore, the sin phi term is appearing in some of the term quantities. So, this is due to change of variable, say r is equal to r 2 sin phi. So, this equation can be easily integrated, and after integration we get r n phi sin phi equal to integration r 1 r 2 into w r cos phi minus w phi sin phi into sin phi d phi plus k. K is a constant of integration. Now, here we get that if we substitute r is equal to r 2 sin phi, then we can write n phi equal to 1 by r 2 sin square phi integration r 1 r 2 into w r cos phi minus w phi sin phi into sin phi d phi plus k. So, this is the equation to find the one of the membrane force n phi, that is in the meridional direction that exists due to self weight. Okay. So, membrane state of stress in the hyperbolic revolution. So, this is the general formulation. Now, we have to come to the our problem, that is the cooling tower, which is a hyperboloid of revolution. So, here the cooling tower is subjected to self weight, that is the gravity load acting vertically, and if this angle is phi, then this angle is pi minus phi. So, component of q along the radial direction is p r, and along the meridional direction is p phi. So, p r is nothing but minus q into cos phi, and p phi from this triangle you can see it will be q into sin phi. So, these two terms will substitute here in this integration. So, p r cos phi, p phi sin phi, and we have obtained this in terms of this gravity load q. So, p r is substituted as q into cos phi, and p phi is substituted as q into sin phi. R 1 is this that we have obtained earlier, and R 2 we have obtained earlier with as this quantity s square divided by s square sin square phi minus b square cos square phi to the power half. So, these two quantities R 1 and R 2 is obtained from the first principle of calculus, and very important parameter is here. Okay. So, after integration we obtain n phi equal to a factor s square sin square phi minus b square cos square phi under root. So, this term is under root, or it can be written as raised to the power half divided by s square sin square phi, and it is multiplied by q a to the power 4 b square integration sin phi d phi s square sin square phi minus b square cos phi. So, that integration has to be done. So, that integration can be done, and tables of integral provides such type of integral. Various integrals are available, standard integrals are available in tables of integral, or it can be done using the principle of integral calculus. Okay. So, integral appearing in equation 17 is taken from tables of integral, and then sin phi d phi divided by s square sin square phi minus b square cos square phi is written as minus 1 by 4 a cube into s square plus b square to the power half, that is this term will be under the square root, multiplied by 2 a s square plus b square raised to the power half into cos phi divided by s square minus s square plus b square cos square phi plus ln. Ln means logarithmic log with a base, natural base. So, ln means natural logarithm. So, ln log of a plus s square plus b square to the power half cos phi divided by a minus s square plus b square half into cos phi. So, this integral, though it is lengthy, but it can be found after integrating this expression. Okay. So, these have to be substituted now in this equation 17. After substituting, we get this n phi equal to s square sin square phi minus b square into cos square phi divided by s square sin square phi, and the numerator has to be under the square root here, into minus q a b square divided by 4 s square plus b square to the power half into this factor have to be multiplied by this quantity. So, 2 a into s square plus b square half into cos phi divided by s square minus s square plus b square into cos square phi plus logarithm of a plus s square plus b square half cos phi divided by a minus s square plus b square half into cos phi. So, this second bracket is closed, and it is to be multiplied by this factor minus q a b square divided by 4 s square plus b square to the power half. So, all this quantity again have to be multiplied by this factor, and then the constant of integration appears. We could not find it till now. So, we will say how the constant of integration can be found out or eliminated. Okay. Now, here you can see the shell at the upper surface is free. So, at phi is equal to phi 1 that you are seeing, the reference plane is this vertical axis of revolution, and at this point the meridional angle is phi 1. So, at this point this shell is free, that means there should not be any stress. So, n phi is 0 at this point. So, therefore, putting n phi to be 0 here at phi is equal to phi 1, we can find k equal to q a b square divided by 4 into a square plus b square to the power half into 2 a multiplied by a square plus b square to the power half into cos phi 1 divided by a square minus a square plus b square into cos square phi 1 plus natural logarithm a plus a square plus b square half cos phi 1 divided by a minus a square plus b square half cos phi 1. So, constant of integration is found out. So, total expression, that is complete expression for the meridional stress n phi is now calculated as q b square divided by 4 a square plus b square half multiplied by a square sin square phi minus b square cos square phi divided by sin square phi, and numerator is under the square root here, under the square root, then multiplied by this term, the under the second bracket you will be seeing that twice a into a square plus b square to the power half cos phi 1. Phi 1 is the angle which is defining the top free edge of the shell, then divided by a square minus a square plus b square into cos square phi 1 bracket closed plus natural logarithm a plus a square plus b square half cos phi 1 divided by a minus a square plus b square half cos phi 1, where cos phi 1 is known quantity because the boundaries of the shell is prescribed. So, we can find the phi 1. The same term is repeated here, you can see, but here angle is phi, that means at any meridional angle phi you can calculate the stress. So, first quantity is coming due to the constant k that is evaluated by imposing the boundary condition at phi is equal to phi 1, and second term you see that it contains the variable phi, and by putting the value of phi you at any meridional angle you can calculate the stresses. Okay. So, that is the expression for the meridional stress n phi. Though it is a long expression, but very useful expression for design of cooling tower. In compact form, let us write like that. We write in compact form n phi equal to a into c plus d minus e plus f. So, a is this quantity q b square divided by 4 a into a square plus b square under the square root into a square sin square phi minus b square cos square phi under the square root divided by sin square phi. C is 2 a into a square plus b square half cos phi 1 divided by a square minus a square plus b square cos square phi 1, and d is logarithm of a plus a square plus b square to the power half cos phi 1 divided by a minus a square plus b square to the power half into cos phi 1, and other factors E is similarly found as C, but you can see here the angle phi is appearing instead of phi 1. So, that at any phi you can put this, but this is a constant term because we impose the S condition at phi is equal to phi 1. S condition at phi is equal to phi 1 was that the n phi is 0 at the free edge. So, imposing this condition we obtain this constant k, and as a result of this we get all these terms. So, f is again same term, but here instead of phi 1 you just substitute it as phi. So, the n phi is known completely. If you know the q, suppose in a RCC shell or a concrete shell thickness is known, then thickness multiplied by the density of the concrete will give you the load per unit area as a self weight of the shell. So, q is known in that way, and other parameter b and a has to be found out from the geometry of the hyperbola. Okay. So, once you obtain this n phi, then n theta you obtain by this equation n phi by r 1 plus n theta by r 2 equal to p r. P r is the radial load, and this load we have seen that we have this resolve the component of q in the radial direction p r, and p r is minus q into cos phi. So, in the equation here p r will be minus q into cos phi, and other quantity n phi that we have obtained just now, this n phi is obtained, we have to substitute it. R 1 is obtained earlier, R 2 is obtained earlier. So, n theta is obtained as R 2 p r plus n phi by R 1. So, n theta and n phi both are obtained now, and we can design the shell or we can analyze the shell. So, let us see some exercise on this hyperboloid of revolution, that is a cooling tower problem. So, a schematic sketch of the cooling tower is before you, and you can see this cooling tower height here is 100 meter, and the axis of the cooling tower is at a distance of 60 meter from the base, and the top is at a distance of 40 meter. Okay. So, let us see what are the some salient features of this cooling tower. The name of the shell is, so first question, the name of the shell is, this name is hyperboloid of revolution, and the shell is a curved shell. What is the type of curve? It may be singly curved, doubly curved, but this type of shell is doubly curved shell. Number 3 question is, shell is synclastic, anticlastic, but here because of the curvature in two opposite direction, we call this shell as anticlastic shell. The equation of the meridian can be defined as x square by s square minus y square by b square equal to 1. Now, asymptotes will intersect the bottom, and at which point the asymptote will intersect the top of the shell from the axis of rotation. So, that we want to find out. Okay. So, the question on the fill up the gaps is answered, and now the last question, the asymptotes of the meridional curves intersect the bottom at this meter or intersects top at this meter from the axis of rotation. Let us find it. Okay. So, this is the question. Now, we know that s square plus b square equal to c square, where c is the distance of one of the foci from the vertical axis of rotation. So, here you can see from the given dimension of the shell, the c is located, focus is located at a distance of 32 meter from the axis of rotation. So, c is 32 meter, and you can see this, the length of the transverse axis is 20 meter, that is A is 10 meter. Okay. So, A is 10 meter. So, therefore, B is found as root over 32 square minus 10 square. So, B is 30.39 meter. Now, knowing the B and A, we can now find the slope of the asymptote. Slope of the asymptote can be found as B by A. So, B by A is 3.039, that is the slope, and if we see that if this is the slope, so angle, and this is the your this consider a triangle now with slope here, that tan phi equal to 3.039. So, at the bottom the asymptote will intersect this base at a distance of 60 divided by 3.039, that is 19.74 meter from the axis of rotation, and at the top it will intersect the top at a distance of 40 by 3.039 from the vertical axis of rotation. Okay. Now, let us see the stress variation or the membrane force variation. So, first let us see how the Gaussian curvature varies along the vertical axis. Now, Gaussian curvature is known as the product of two principal curvatures. So, radius of curvature R 1 and R 2 are obtained. So, we can now find the Gaussian curvature as 1 by R 1 into 1 by R 2. So, that variation we have to show along the vertical axis. Then second question is find the membrane forces under the self weight and show graphically its variation along the vertical axis. Given the material of the shell is RCC with concrete M30 grade. So, M30 grade concrete will be the permissible stress in bending compression will be 8 Newton per mm square. Thickness of the shell is 150 millimeter and the steel is not specified here, but we can find the steel area also. For example, steel can be taken as Fe 415 whose permissible stress is 230 Newton per mm square. Then find the value of strain along the meridional and circumferential direction at point on the shell located at y equal to 0. Okay. So, that means y equal to 0 if this is the origin. So, y is equal to 0, that means you have to find that y is equal to 0 and at this distance you can find at 10 meter. Let us see the variation of Gaussian curvature. So, Gaussian curvature varies like that, and you can see that the Gaussian curvature is negative and the value of Gaussian curvature is tabulated here. If it is 0 at 10 meter intervals above the top and 20 meters interval above the towards the bottom, we have tabulated this, and then this Gaussian curvature is written here. So, you can see that at 0 the Gaussian curvature is 0.0011, that means at the center of the hyperbola. Okay. So, now let us see the meridional force along the height of the shell. Meridional force is n phi, and along the height if I plot it, you can see here that up to say this region all forces are compressive in nature, and maximum forces you can see here say around say 180, around 180, and this is also tabulated here, tabulated in the second table. So, meridional stress at here say 190 for example. So, 190 if it is a stress force kilonewton per meter here, then in Newton millimeter it will be 190 Newton per millimeter, and if the thickness of the shell is say 150. So, 190 divided by 150. So, that ratio is far less than the permissible compressive stress in bending compression in concrete of grade M30. Permissible stress in bending compression of concrete of grade M30 is taken as 8 Newton per mm square, and we are getting the induced stress, compressive stress maximum as say 190 by 150. 190 by 150 is again very low quantity, it is less than 2. So, the structure is safe in regard to the compressive stress of permissible compressive stress of concrete. Now, if you want to see the n theta variation, you can see this how the n theta varies, and you can find the n theta becomes tensile, that is negative in some of the regions. So, here we will get this tensile stress, and one thing is that if this is the maximum stress, then based on that you can also find the quantity of reinforcement. Quantity of reinforcement can be found, suppose if you know the force per unit length, then maximum force per unit length, that is of tensile nature, divided by permissible stress in tension of steel. So, that is taken as 230 Newton per mm square. So, that quantity will give you the area of steel per meter length. So, area of steel in millimeter square per meter length. Now, choosing a diameter of the steel bar, generally in thin structure, here the thickness is 150 mm. So, maximum you can provide the thickness bar diameter from 8 mm to 12 mm within this. So, you can see the spacing of the reinforcement will also not be very large, requirement of reinforcement will be less. So, that means here suppose capital AST is the required area of the steel and small AST is the area of one bar that you choose, the diameter of the bar either 8 mm or 10 mm or 12 mm. Then the spacing of the steel can be found as small AST into 1000 divided by capital AST. So, that is the spacing of the bar in millimeter center to center. So, that is found based on the area of steel that we have calculated depending on the maximum tensile stress that is found in this table. So, maximum tensile stress is found in the table is very low that you are seeing here, and therefore, the requirement of reinforcement will also be low. So, the requirement of reinforcement and checking the thickness of the shell, adequacy of the thickness of the shell, so that the induced compressive stress remains within the permissible limit. That type of problem I have earlier demonstrated in case of spherical dome. So, same principle can be used here to check the safety of the shell in regard to its thickness and also to specify the reinforcement requirement in the shell. Okay. So, this is the analysis of the hyperboloid of revolution, which is a very important structure in thermal power station, and obviously, it is falling under a doubly curved anticlastic shell, and that is a shell of surface of revolution. Okay. So, let us see the summary of today's lecture. So, in this lecture, membrane analysis of a hyperboloid of revolution, which is anticlastic shell, has been presented. The example of a cooling tower subjected to self weight is given. Thank you very much.